previous class, we studied about electromagnetic theory regarding electromagnetic radiations, isn't it? That is about the classical physics. Now in today's class, we are going to study first the drawbacks of electromagnetic theory. The electromagnetic theory could not explain. First one is the nature of the nature of emission of radiation from hot bodies. Okay, hot bodies emit radiation and that phenomenon is called as black body radiation. The electromagnetic theory couldn't explain about black body radiation. That is the first drawback. Next point is, it couldn't explain about photoelectric effect. What is photoelectric effect? It's a phenomenon of ejection of electrons from a metal surface when radiation strikes it. Simply, when a radiation strikes on a metal piece, electrons will be ejected from that. That phenomenon called photoelectric effect could not be explained by what? About the electromagnetic theory. That theory couldn't explain about photoelectric effect. Next point or the drawback of that theory is, it couldn't explain the variation of heat capacity of solids as a function of temperature. That is, how the heat capacity, ability or the capacity of solids to bear the heat couldn't be explained as a function of temperature. The electromagnetic theory couldn't explain the variation of heat capacity of solids as a function of temperature. How temperature affects the heat capacity of solids. And also, the electromagnetic radiation theory couldn't explain the line spectra of hydrogen atom. Line spectra of hydrogen atom. About that we will study detail in the upcoming classes. These are the main 4 drawbacks of electromagnetic radiation theory. We will study about each phenomenon in detail. The first phenomenon that we are going to discuss is about black body radiation. What is black body radiation? An ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body. Okay, it's an ideal case or an ideal body that can emit and absorb radiations of all frequencies in a uniform manner is called a black body radiation or a black body. It's an ideal case, an ideal body that emits and absorbs radiations of every frequencies in a uniform manner, and that radiation emitted by a black body is called black body radiation. The radiation emitted by an ideal black body is called as black body radiation. This phenomenon of black body radiation was first mentioned by Max Planck. Okay, the phenomenon of the black body radiation was given by scientist Max Planck in 1900. So what we learned? A black body is an ideal body that emits and absorbs radiations of all frequencies uniformly. Next, about black body radiation in detail. You may have seen an iron rod, isn't it? An iron rod, that picture is seen in the image. An iron rod that is heated in a furnace. First, what happens when an iron rod is heated in furnace? It first becomes a dull red color, isn't it? Then becomes more and more red as the temperature increases. It becomes white and then becomes a blue color, isn't it? First it becomes a dull red color, isn't it? Then it becomes more and more red. As the temperature increases, it becomes a white color. Then turns into a blue color as the temperature becomes very high. This means that red radiation is the most intense at a particular temperature and the blue radiation is more intense at another particular temperature, isn't it? At a particular temperature, we see the blue color. When the temperature goes on increasing, the color changes, isn't it? That is the inference that at a particular temperature, the blue color is intense and another particular temperature, the red color is the most intense color when we are heating an iron rod. What we can infer from this? Intensities of radiation of different wavelengths emitted by a hot body depend upon its temperature. Okay, intensities of radiation of different wavelengths emitted by a hot body always depends upon the temperature. That is, intensity depends upon temperature. This is a graph that relates what wavelength and intensity relation. Look here, wavelength is in x-axis and the intensity of the color is shown in the y-axis. Okay, at two particular temperature the experiments are conducted. One at a temperature T2 and another at a particular temperature T1. Okay, at a particular temperature T2 and another at a particular temperature T1. And a T2 temperature is greater than T1 is given in the diagram. Okay, the red is at a higher temperature compared to the blue line. T2 is the red line and T1 is the blue line. So, at a given temperature, the intensity of radiation emitted increases with the increase of wavelength. Okay, when we are considering at a particular temperature T2, the intensity first increases, isn't it? The intensity goes on increases with the increase of wavelength and reaches a maximum value, that is this maximum value at a given wavelength and then starts decreasing, isn't it? At a particular temperature T2, first as the wavelength increases, intensity goes on increases, reaches a maximum and then it goes on decreasing with the increase of wavelength. Also, as the temperature increases, maxima of the curve shifts to a shorter wavelength, isn't it? When temperature increases from T2 to T1, okay, from T2 to T1, or from T1 to T2, okay, T1 is at a lower temperature compared to T2. When the temperature increases from T1 temperature to T2, what happens? The maxima wavelength, okay, here in the T1 case, the maxima wavelength is in between 1000 and 2000, but at a T2 temperature, the maxima is below what? 1000 lambda, 1000 nanometer. So, what this infers? As the temperature increases, the maxima of the curve shifts to a shorter wavelength. Okay, as the temperature increases, the maxima shifts to a shorter wavelength. At a smaller temperature, at T1, it is at 2000. The maxima is in between 1000 and 2000, but a higher temperature, it shifts to a smaller wavelength, that is below 1000 nanometer. So, next about Planck's quantum theory. Okay, Max Planck scientist developed the Planck's quantum theory. Max Planck assumed that radiation could be subdivided into discrete chunks of energy. Okay, radiation. We already studied about electromagnetic radiation. What Max Planck told us that radiation could be subdivided into what? Discrete chunks of energy. He suggested that atoms and molecules could emit or absorb energy only in what are discrete quantities, not in a continuous manner. That is, radiation, he told that radiation is not continuous, okay, but as discrete quantity. It is not a continuous, the radiation is emitted not in a continuous manner, but as small chunks of energy or small packets of energy is what proposed by the scientist Max Planck. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. First, he told that radiation is not continuous, it is not emitted continuously but as discrete quantities. And for that discrete quantity, he gave the name what? Quantum. Quantum is what? The smallest quantity of energy that can be emitted or absorbed. Okay, the smallest quantity that can be emitted or absorbed in the form of energy is termed as quantum. The energy E of a quantum of radiation is proportional to frequency nu and is expressed by the equation what? He told that E is proportional to frequency, that is energy is proportional to frequency. E energy is proportional to frequency, that is denoted by what? A symbol nu. Okay, that is in the form of V, nu. Okay, energy proportional to nu is the name of that and it is frequency. Or to change this proportionality constant, we can write it as E is equal to what? H nu. Okay, H nu, and that H is a proportionality constant and it is known as the Planck's constant. Okay, small letter h is called as Planck's constant and the value of Planck's constant h is 6.626 into 10 power minus 34 joule seconds. Remember this value, the Planck's constant value, we need that value for in problems. Okay. Let's now summarize the assumptions of Planck's theory. Okay, the assumptions made by Planck's. First point is each radiation is always associated with what? A definite amount of energy and is known as radiant energy. That is the first assumption. Then radiant energy is absorbed or emitted in the form of small packets of energy called quanta or quantum. Quantum, small packets of energy called quantum or quanta we can say. Each wave packet or quantum, okay, each wave packet or energy packet or quantum is associated with a definite amount of energy called photon. Okay, energy is emitted in the form of packets called as quanta and that wave packet or quantum is associated with a definite amount of energy called photon. Next point. The amount of energy associated with the quantum of radiation is proportional to frequency. Already we studied the postulate energy is proportional to frequency of radiation nu. That is E is equal to h nu, small letter h nu, where h is a Planck's constant and nu we already studied in the class electromagnetic radiation. Nu is equal to C by lambda. So h nu is what? hc by lambda. So energy equation is what? H nu which is equal to hc by lambda. Next point is the energy emitted or absorbed by a body is always an integral multiple of quanta or quantum. Okay, energy will be integral multiple of quantum. That is, we studied energy is not continuous. E is equal to nh nu. That means n can be 1, 2, 3. So how will the energy be? Energy of radiation be? It will not be continuous. It will be how? It will be h nu, 2h nu, 3h nu, like that the energy will be distributed. Okay, not the energy is emitted continuously, it is emitted like h nu, 2h nu, 3h nu, etc. These are the assumptions made by Planck in his Planck quantum theory. Now let's do one problem related to black body radiation. First question. Calculate and compare the energy of two radiations, one with a wavelength of 300 nanometer and the other with a wavelength of 600 nanometer. How we will solve this question? We got what the wavelength value. 1 with lambda 1 is equal to 300 nanometer. Lambda is a representation for wavelength. So, lambda 1 is 300 nanometer. We need to compare the energy. The equation for energy we studied, E is equal to h nu, isn't it? But the frequency nu value is not given. So, we can write it also as hc by lambda, isn't it? C value is the wavelength of light, and also h is Planck's constant and lambda is the wavelength. So we can substitute, isn't it? We know the lambda 1 value, h value and c value we know. So substitute it. 6.626 into 10 power minus 34 joule second is the value of h. C, velocity of light. Okay, C is the velocity of light. That is 3 into 10 power 8. 10 raised to 8 meter per second or meter second inverse. Divided by what is the lambda 1? It is 300. So, 300 into 10 raised to minus 9 meter will be the value, isn't it? Lambda is given as 300 nanometer, isn't it? We need to convert it to meter because the whole energy value we need in what? Joules. So we need to convert the lambda value into meter. Okay, 1 nanometer is how much? 310 power minus 9 meter. 300 into minus 9 meter. We converted nanometer to meter. So, calculate the value. You will get like approximately 3.313 into 10 power minus 19 joule or 10 raised to minus 19 joule will be the energy value of lambda 1. Next, lambda 2 also is given, isn't it? Lambda 2 is what? 600 into or 600 nanometer, that is equal to how much meter? 600 into 10 power or 10 raised to minus 9 meter. Energy E is equal to h nu is equal to hc by lambda is the equation. Substitute the value 6.626 into 10 power minus 34 into C is what? 3 into 10 power 8 meter per second divided by lambda value is 600 into 10 raised to minus 9 meter. And the answer you will get is what? It is 3.313 into 10 raised to minus 19 joule. Okay. The last one, the value will be what? There is a slight change. It is 6.626 into, it will be what? 6.626 into 10 raised to minus 19 will be the value of E1. Okay, this is E1. And E2 value will be what? 3.313 into 10 raised to minus 19 joule. Just calculate and tell. Okay, so E1 and E2 we got. So, just to find the what? Ratio of E1 and E2. Okay, E1 and E2, just find the ratio. E1 by E2, you will get it as 2. Okay. E1 value divided by E2 value will be 2. So that is the answer. Just compare the energy values of E1 and E2. E is equal to h nu or which is equal to hc by lambda. That equation you need to solve this question. Next question. Calculate the energy of 1 mole of photon. Calculate the energy of 1 mole of photon of radiation whose frequency is 5 into 10 raised to 14 hertz. Frequency means nu. Okay. The question, frequency is given as 5 into 10 raised to 14 hertz is given. We need to find the energy. First find the energy. E is equal to h nu. H value is what? 6.626 into 10 raised to minus 34 into frequency value is what? 5 into 10 raised to 14. And you will obtain the value as what? 3.313 into 10 raised to minus 19 joule will be the value of energy. But in the question, energy of 1 mole of photon is asked. Okay, 1 mole of photon is asked in the question. So what you will do is energy of 1 mole of photon. So the value energy of 1 mole of 1 mole of photon is equal to what? E into photon is equal to Avogadro number, 1 mole, isn't it? Avogadro number, that is Na into the energy value, that is 6.022 into 10 raised to 23 into the energy value, that is 3.313 into 10 raised to minus 19 joule. So you will obtain it as 199.51 kilojoule per mole, or kilojoule mole inverse will be the energy of 1 mole of photon. Okay. First we found the value of energy using the equation E equal to h nu. Already in the question frequency is given and we need to know the value of Planck's constant. 6.626 into 10 raised to minus 34. We will multiply the value and we will get the energy in joule. But in the question it is asked that of energy of 1 mole of photon. So we will multiply the energy value that we obtain with what? Avogadro number. Avogadro number is 6.022 into 10 raised to 23. Into our energy value we will substitute and we will get the value in joule per mole, change into kilojoule per mole. Just calculate the values and tell if there is any mistake. Okay, so in today's class we studied about what are the limitations of electromagnetic theory, then about black body radiation, how the intensity and temperature is related in the emission of radiation. Next important thing was Planck's quantum theory. Okay, the postulates and the assumptions we studied, and also the main equation, energy is emitted in the form of quantum. That energy is equal to h nu. H is Planck's constant and nu is the frequency. And remember the Planck constant value 6.626 into 10 raised to minus 34. H nu can be also written as hc by lambda, where nu frequency is equal to c by lambda. C is the velocity of light, that is 3 into 10 raised to 8. Okay, c value is 3 into 10 raised to 8 meter per second. Lambda value will be given. Lambda value is the wavelength of radiation that we are using. Okay, dear students, that's all for today. Hope it's clear for you. In the next class, we will study about photoelectric effect. So, thank you everyone. Thank you and have a nice day.